Okay, so welcome to the Oxford Discrete Maths and Probability seminar. This week it's a pleasure to have Michelle Delcourt, who's going to talk on hypergraph matchings, avoiding forbidden submatchings. Thanks, Michelle.
Yeah, Alex, and thank you, Christina and Alex, for inviting me. I'm very pleased to be here. I should mention that all of the work I'll be talking about today is joint work with Luke Postle at the University of Waterloo. All right, so let me maybe begin by asking a bit of a broad question. So in general, when could we hope to find a large matching in a hypergraph avoiding certain submatchings? And here, by large matching, I'm really thinking about a perfect matching or an almost perfect matching in a hypergraph. And we'll be talking about various conditions that we need to impose on the hypergraph in order to find, first of all, large matchings, but then large matchings with additional restrictions, in particular avoiding certain sub-matchings. So to this end, let's introduce the following. So let's have a hypergraph called G. And for this hypergraph, I'm going to define what I'm going to call a configuration hypergraph H. And here I am encoding the edges of G as vertices of H, and I will throw an edge into H that consists of matchings from the original hypergraph G. And here I'm just going to be doing the interesting matchings, ones that contain at least two hyperedges. And in this context, I'm going to say that a matching of the original hypergraph G is going to be H avoiding if it spans no edge of this hypergraph H. So there's this related concept, somewhat related concept, that's familiar in the literature that we call a line graph. So just to refresh your memories, a line graph of a hypergraph G is going to have the vertex set consisting of edges of G, and we're encoding incidences here. So we're going to throw in an edge, and this is an honest to goodness graph here. We're going to throw in an edge if the intersection is non-empty of the edges in our original hypergraph G. So we're encoding incidences in our original hypergraph G here. So in this context, thinking about matchings avoiding certain submatchings, we could also be thinking about looking at independent sets in the line graph of G union H. So it might be convenient to think about independent sets in this other graph, this other hypergraph, or matchings that avoid H. And so in this context, we're interested in what conditions the line graph union H under what conditions will this have independence number about the minimum of the independence numbers of its components. So an even more general question, can we a more ambitious question? So already it's difficult to find large matchings in hypergraphs, even for uniform hypergraphs. It's sort of NP complete to see if you can find a perfect matching. And in graphs, it's a bit easier. There are nice characterizations for finding matchings, but for hypergraphs, it's a bit hard. So already finding matchings avoiding submatchings is ambitious, but furthermore, could we almost decompose the edges into large H avoiding matchings? Well, if we're thinking about things in the context I mentioned before, this is somehow, instead of looking at one independent set, we're actually looking at colorings in this line graph union H. So here we're kind of thinking about the chromatic number of the line graph union H. So we could ask about when does the chromatic number about the maximum of the chromatic numbers of the components. So I want to state our main technical result and then back up a bit and say a little bit about what it implies. To this end, let's just define a couple of things. So when I'm talking about codegree of vertices, of pairs of vertices in a hypergraph, I'm talking about the number of edges that they jointly extend to. So you fix a pair of vertices and you think about the number of edges that contain both. And in the context of hypergraphs, when I'm talking about girth, I'm talking about the smallest integer for which we have a Burge cycle. And I'm going to denote the I degree by d sub I of v. So this simply means the number of edges of size exactly I that contain our vertex v. So one of the difficulties here is when we're dealing with this configuration hypergraph in practice for some of our applications, it may not be a uniform hypergraph. So we might really have to think about how many edges of certain sizes each vertex is contained in. And that's going to be one of the difficulties that we deal with. So I'm going to mention the main technical result and then really talk a bit about a number of nice applications and sort of what it means. So this is a bit technical. Let me just say formally what I mean. Again, all of this is available on arXiv if you want to check out the details of the proof or some of the other statements. So we're going to be dealing with R uniform hypergraphs on n vertices. So that's our initial graph G. And we have some mild conditions on G. We have bounded maximum degree, and we also have some bound on the codegree. So in terms of the maximum degree, and our configuration hypergraph, the things that, so we're in this context, we want to find a matching in G, a large matching in G. In practice, we can encode a lot of interesting problems as matchings in certain auxiliary hypergraphs. And in this setting, we're thinking about the forbidden submatchings as encoded in this configuration hypergraph. And we're going to say that our configuration hypergraph has girth at least 5. Each edge containing at most G vertices. Here we're not a uniform hypergraph, but we should have a bounded size on our edges. And we have maximum I degree for each I, bounded in terms of the max degree of our original graph. And if we have all of these conditions, then we can say something about the chromatic number of the line graph of G union H. And furthermore, we prove something even stronger. We prove for the list chromatic number as well. If you know what that is, it's just a generalization of the chromatic number. We prove something a bit stronger, that this is bounded above by 1 plus d to some error term times d. Okay, so we'll come back to this in just a second, and maybe let me explain a bit about what this implies. This is actually a very, very general statement, a very general framework, and we'll talk about some of the applications. So historically, a lot of related questions have gathered a lot of interest. And let me just think about this in 2 very broad categories. So first of all, let's think about our configuration hypergraph having no edges. So what does this mean? Well, we are not forbidding anything. We just want to find large matchings. And I've said this already is a bit of an ambitious undertaking. So what does this mean? Well, essentially, morally, we're saying something along the lines of Pippenger-Spencer. So our codegree conditions are a little bit different, but morally, we're saying that we have a uniform hypergraph with bounded max degree and bounded codegree conditions. And then we can find independent set in the line graph of very large size. And this is sort of codifying, sort of encapsulating nibble type results from design theory. So I'll say a bit more about this in a few minutes. So this historically is one train of research beginning in the 1980s. And a very, very celebrated result was, instead of doing this for a chromatic number, doing this for list chromatic number in the proof of the asymptotic version of the list coloring conjecture by Kwan. So morally, if we have no restrictions, then we're trying to find a large matching or a large independent set in the line graph of G with these mild conditions on G. What if, alternatively, the line graph of G has no edges? Well, this also is very, very interesting. So when G is a matching, right? I said the line graph is encoding incidences. And so if there are no incidences recorded, well, then our graph itself is a matching. And in this context, we can think about our uniform hypergraphs on n vertices with girth at least 5 and maximum degree delta, and people study the size of independent sets in this context. The first really result in this vein was Ajtai, Komlós, Pintz, Szemerédi, also from the 80s. And there have been a number of subsequent improvements to this theorem in this vein. So looking at so-called linear hypergraphs with girth at least 3, was shown by Duke, Leffman, Rodel. And instead, looking at the chromatic number was done by Fries and Mubai, in addition to also being girth at least 3. In addition to all of these things, throwing in bounded codegree condition was done by Cooper-Mobai. And all of these things, but instead of looking at our uniform graphs, but actually at graphs with mixed uniformities, was very recently done by Lena Lee and Luke Postle. And really thinking about these things with mixed uniformity is going to be key in our proof. We really do need that for our applications. So we actually show something very strong in this vein as well. So we show all of this except not with this girth 3 condition. So we're able to do mixed uniformity, girth at least 5 in our main technical theorem. And so I want to say a few words about the proof ideas here. And there was this really lovely survey about the Nibble method that came out, I think, in December of 2021. And there was this really nice quote. These two threads of research, edge coloring, vertex coloring, with the Nibble method, have developed somewhat in parallel, somewhat intertwining. And really fundamentally, we are showing that these two streams of research actually are somehow morally the same, have commonalities. And there are a few keys to this very general theorem. So we have to do mixed uniformities for H, and so we have to introduce what we're going to call a weighted degree and track it in order to really overcome this. And we're doing fundamentally a Nibble type technique. So in general, if you haven't seen Nibble type proofs before, they're really lovely. There's a really nice treatment of them in Ella and Spencer that I'd encourage you to go look at. But in general, you're trying to find a large matching, a large independent set, some large structure, and that's a bit ambitious in the entire hypergraph. But provided you have some nice conditions, you could, instead of analyzing the entire thing and finding a large one all in one go, you can sort of look at a random subset of the edges, and then within there, sort of digest what you've found, find a large matching, peel off some additional edges, maybe do a little cleaning, and then you have to prove some things about what's remaining, that you have the number of edges you were expecting, and they're sort of distributed how you like, and then you can iterate this process. You can go and nibble again and digest another portion of the hypergraph and keep going. And really, this sort of very intuitive idea, this iterated algorithm for processing the hypergraph and obtaining almost perfect matchings or large independent sets is really fundamental. It's a very, very intuitive idea, and it has been used. I mean, even in the proofs of the gaps in the primes, they do something akin to Pippenger Spencer on an auxiliary hypergraph. There are lots of really lovely applications if you define your hypergraph appropriately. And here, somehow doing the nibble simultaneously on the line graph of G and on H, it's a very delicate calculation, but it just actually works out really nicely. But to this end, in order to do the concentrations, we have to introduce a new version of Talleyrand's inequality. And then we just finish off using the local lemma. So I wanted to say a few words about some of the applications and some of the things that we've been able to do in this very general setting. So I might back up a little bit and say our first application. So generally, we weren't initially thinking in this broad of a context. We were thinking about Steiner systems. So this really, really lovely paper appeared in January of last year that really set into motion all of this research. So let me say a few words about Steiner systems. So what do I mean by a Steiner system? Well, we're going to say that an NQR system is going to be a collection of Q element subsets from some N element ground set with the property that every R element subset lives in at most one of our Q element subsets. It's a bit of a mouthful. I'll do an example in a second. So the partial ones are collections of Q element subsets, and the largest possible ones are going to be full Steiner systems or just NQR Steiner systems, the ones that contain actually the largest number of Q element subsets that they could N choose R over Q choose R. So in other words, every R element subset lives in at exactly one of these Q element sets. So in particular, when Q is 3 and R is 2, we call these Steiner triple systems, which in and of themselves have attracted a lot of attention. So for instance, on 7 vertices, we have the Fano plane. So here we can think about our hyperedges corresponding to lines. So we have a 3 uniform hypergraph on 7 vertices, where with the property that any 2 vertices from the ground set live in exactly one line, live in exactly one hyperedge. So this is an example of a 7-3-2 Steiner system. And these are an example of designs. And the natural question in this area is, when do these things exist? Now, there are several sort of obvious necessary divisibility conditions, but if we assume those, when exactly do these things exist? So of course, this is the notorious existence conjecture. Namely, for n sufficiently large, we hope to find these things whenever these divisibility restrictions hold. And of course, there's been lots of progress on this. So it's been fully resolved, in fact, using both algebraic techniques and purely combinatorial methods. But I really wanted to mention that along the way, a lot of really nice tools and techniques and a lot of good people have worked on the existence conjecture. In particular, the first instance of the so-called nibble method was Rödel's proof of the approximate version of the existence conjecture, the so-called Erdős-Hanani conjecture, was the sort of first use of the actual nibble technique. So it's maybe not a surprise that the nibble is coming up here as well. So you may be asking, well, that's all well and good, but it's fully resolved. What else is there to do in Steiner systems? So I want to define a JI configuration. So here I is the number of Q element subsets and J is the number of vertices. A JI configuration is a set of I hyperedges spanning at most J vertices. And here we're dealing with a Q uniform hypergraph on N vertices. So Erdős and others observe that for every fixed I, we have a lot of structure. A triple system should have an I plus 3I configuration for every fixed I. And given this observation, Erdős asked a question, well, what about I plus 2I configurations? What exactly is going on here? So Erdős conjectured that for every G, there should be some n sufficiently large where we can find triple systems with no I plus 2I configurations for all I between 2 and G. So let me introduce one more definition. So let me introduce a concept of girth in a Steiner system. So let's say that the girth of a Steiner system is the smallest G for which it has a G plus 2G configuration. In this context, Erdős is asking, provided we're admissible for n sufficiently large, we would like to find a triple system with arbitrarily high girth. And this is sort of one of the beginning results in what Leniel has popularized as high girth combinatorics. So taking well-known combinatorial objects and then asking, well, with the appropriate notion of girth, do ones with arbitrarily high girth exist? So the answer here as well is, well, yes, and this also is fully resolved. So this was fully resolved in January, and this lovely paper was sort of what got us thinking. So I should mention that the approximate versions were a few years earlier by Bohman and Warnke and Glock, Kühn, and Osthus independently. And they're using some sort of randomized greedy approach here. So they're not using the nibble method per se, but they're using more of a randomized greedy approach. Whereas Kwan, Sawhney, and Simkin are using iterated absorption and a lot of heavy machinery to take the approximate version, to use Bohman and Warnke's result in particular, and extend it to the full conjecture. So it's a really lovely paper and really a breakthrough result. So we asked, well, what if you simultaneously ask Erdős's question and the existence conjecture? So what about Steiner systems in general, not just the triple systems, but Steiner systems in general? And of course, other people have thought about this. So Glock, Kühn, and Osthus found the appropriate notion of girth in this context. So here they show that these things contain I, Q minus R plus 1 I configurations for every fixed I, which is exactly the analogous thing to these I plus 3I configurations. And so this is the natural notion of girth. And they conjecture that the simultaneous generalization of the existence conjecture and Erdős's triples of arbitrarily high girth should be true, that for sufficiently large n, we should be able to find NQR Steiner systems of arbitrarily high girth whenever n is admissible, and this was reiterated by Kivash and Long. And our main result is to show the approximate version. So in other words, we can find partial NQR Steiner systems of size 1 minus some error term times what the full ones would be that have no I, Q minus R plus R, I configurations for I between 2 and G. And here we spent a lot of work. We were very careful here that this error term is a polynomial in n, which is what you would need to prove the full result if you could figure out the correct notion of the iterated absorbers and really get it to work in general. This is what you would need. So independently, another group obtained the same results using a different proof. And I'll maybe say a few words about both of our proofs. So again, our proof technique is a nibble type proof, whereas their proof, you can think of it as a randomized greedy process. You can think of them doing some sort of randomized greedy process with independent sets on the line graph union H. And theirs morally is very similar in approach to Bohman and Warnke's approximate version. So you can think of ours also as a nibble proof of Bohman and Warnke's results. So I should say that we prove something a bit more general that implies a number of other applications that theirs does not, and I'll talk about those if I have time. However, there's a bit of a trade-off. Their techniques are very nice, and some of the applications they had in mind were counting applications that we are not able to do with our techniques. So it would be an interesting question if you could do a bit more analysis on the nibble to see if you could actually get the same counting type results that they do. But I'll talk a bit about some of the applications in a few minutes. So you may be thinking to yourself, well, okay, this is all well and good. We're talking about Steiner systems now, and we were talking about matching. So what do Steiner systems have to do with matchings and hypergraphs? And if you've seen the original proof of the Erdős conjecture, Rödel's original thing, it is a bit obvious, but in case you haven't, let's go through it because the auxiliary hypergraph is really lovely. And with these things, again, finding matchings and hypergraphs is a very general, broad setting. And sort of once you start seeing matchings and hypergraphs, you start seeing them everywhere, and you start seeing everything in this context. So let's talk about the proper auxiliary hypergraph. So we're going to have as a vertex set all R element sets of some ground set 1 through n. We're encoding here where we would like our Steiner systems, our partial Steiner systems, to be matchings in our hypergraph G. So we're going to throw in as vertices all of our R element subsets. And for each Q element subset, we are going to throw in an edge. So we are going to collect all of the R element subsets that live in this Q element subset. So for each Q element subset, we're going to throw in an edge with Q choose R vertices. And here in this context, when we're dealing with a perfect matching, we will get a Steiner system. And if we have a large matching, then we will get a large partial Steiner system. We are thinking about exactly which Q element subsets to take that don't overlap. And what does that mean? Well, that means that each R element subset lives in at most one Q element subset. So here, matching is exactly the right concept. And it's on this hypergraph that Rödel ran his original nibble. And so finding a large matching in this hypergraph corresponds to finding a large partial Steiner system. So we take this hypergraph and we want to, well, maybe I should just prove a few things to you to maybe convince you that you actually can apply the results that we want. We are uniform. Each edge has Q choose R vertices in it. We are also regular. So if we think about one fixed R element subset, how many edges it lives in, well, there are n minus R other elements in the ground set to pick from, and we're thinking about the Q element subsets that this fixed R element subset lives in, so we choose Q minus R other elements. So we're regular, and if we think about two vertices in this hypergraph, they have low codegree. And why is this? Well, sort of the worst case scenario is when the two subsets share most of the same elements. So when their intersection is R minus 1, because then they'll jointly extend to the most possible additional things, but they still can't extend to too many in terms of the degree of the hypergraph. So here we have the conditions that we need in order to apply some sort of nibble type argument, but what do our forbidden configurations become in this context? So we say that a vertex in H is an edge in G, and a Q element subset. How many edges of H of size I is it in? Well, we can do a calculation, and the things that we want to forbid are these configurations, these I, Q minus R plus RI configurations. And it's not so hard to actually count these and see that the I degrees are what they should be. And you can check a number of the other conditions to make sure that we can apply our main technical lemma. For interest of time, our main technical lemma applies, and we can find matchings that avoid H. In fact, we can say even more. In this language of thinking about independent sets in the line graph instead of matchings in the original graph, we can not only find matchings that avoid H, well, we can actually decompose these into approximate high-graph Steiner systems, which is, I think, a nice result. So let me really, I know that we don't have much time left, but let me say a few words about actually our more general theorem that implies our main result, because it might not seem at first glance that it does, but this is really why we're able to do a number of the applications that the other group is not, and this is really fundamentally why we have such a general result. So really, we're thinking about bipartite hypergraphs. And even within bipartite hypergraphs, finding even 3 uniform bipartite hypergraphs, finding large matchings is computationally difficult. So here, what do I mean by bipartite? Well, it's a generalization of being bipartite for graphs. We're having a partition of the vertex set into 2 parts, A, B, where each edge of G contains exactly 1 vertex from A. So this is a generalization of what it means to be bipartite in the graph setting. And I'm going to say that a matching is an A-perfect matching if it saturates A, if every vertex in A is covered by some edge in our matching. And again, each of these edges contain exactly 1 vertex from A. So we have only cross edges between A and B, but with the property that each edge contains exactly 1 element from A. And it turns out that this very general setting, especially with some of the other applications we had in mind in list coloring and coloring in general, is really handy. So in this context, we show a very general result about finding A-perfect matchings. So essentially, we have a bipartite R-bounded hypergraph with bounded codegree and maybe slightly mismatched degrees. So within A, all the degrees are at least this, and within B, all the degrees are at most this. And to our knowledge, this is the first time that this type of theorem has appeared in the literature. So Penny Haxel and Aharoni and a number of people have studied various conditions on bipartite hypergraphs with various degree conditions and finding large matchings. But this is a surprisingly useful theorem that implies our main result. And why does it do that? Well, we can encode a special hypergraph. So the configuration hypergraph subject to the conditions of our main result, and we will find an A-perfect age-avoiding matching of G. So how are we going to do this? Well, the hypergraph we care about, we are going to have a hypergraph, and it has a list assignment on its edge set. And now we're going to consider the following auxiliary hypergraph. So we have A, and we have B, And we are going to have A be the edges of G and B be these vertex color pairs. So this is slightly clever definition, but once you see how to encode these auxiliary hypergraphs, this is the real power in the theorem, is that, you know, in defining these hypergraphs correctly. So we're going to throw in vertex color pairs, where the color is coming from the list of the edges. So we're going to throw in E itself and all of the colors in the list of E. So in other words, we're throwing in these color pairs for each edge, and we are also marking them with the edge itself. And the whole point here is we want to find an A-perfect matching. We want to find a matching that saturates the edges. So really, we're thinking of finding a list coloring of our edge set of our original hypergraph G. So this context is really handy, and there are a lot of very natural applications, especially when dealing with things like rainbow matchings and bipartite graphs, even not even the hypergraph case, but just thinking about bipartite graphs. And a lot of the auxiliary hypergraphs end up looking something like this, where you're taking sort of vertex color pairs and extending them with the edge or various things. So just a couple of applications, and I'm going to go by a bit quickly because we don't have much time left. But for instance, one area that there have been a number of questions asked about the so-called high girth version of, and you may well ask, well, what does it mean to be a high girth Latin square? Well, a Latin square is an n by n array with n different symbols, each occurring exactly once in each row and each column. And in this context, we might ask to avoid certain sub-configurations. So an intercalate is, for instance, is a 2 by 2 sub-Latin square. So here would be an example of an intercalate. So for instance, you could ask about, can we find ones with no 2 by 2 subsquares, or 3 by 3 subsquares, or k by k subsquares? And so the appropriate thing to do is form a 3 uniform hypergraph encoding rows, columns, and symbols. And in this context, if we find a matching in this context, then it's going to correspond to assigning symbols or coloring the entries in our n by n Latin square. And so approximate high girth Latin squares exist. In fact, more is known by other people than that, but what was unknown is that approximate so-called high girth permutations exist. So you could ask the same instead of by n squares, you could ask by n by n by n, and higher dimensional things without certain sub patterns. And we could also look at, for instance, in honest-to-goodness graphs, we could ask about finding so-called rainbow matchings. So a matching is rainbow if each edge receives a different color. And here, the hypergraph or the graph is colored and maybe not necessarily properly. So it depends on the problem. But the idea is you want to find rainbow matchings and large ones, but here you want to find them with every color of your coloring. So for instance, if you color this with 4 colors, this would be a full rainbow matching. And so we're able to make improvements on a number of problems in rainbow matchings. So here's some nice conjectures that are a bit difficult. So with bipartite graph, here properly edge colored with Q colors, each appearing at least Q+1 times, then we would like to find a rainbow matching with all Q colors, or for non-bipartite graphs, with each color at least Q+2 times, finding one with Q colors. These are really hard, but you could ask natural weakenings. So finding slightly smaller rainbow matching, assuming the colors appear more times, or assume that the number of colors is slightly more. And we are able to do a number of things. Maybe in the interest of time, I will skip the actual statements. If there are questions, I can go back. But I just wanted to say that really our main theorem sort of shows a common generalization of two very classical streams. So in general, finding almost perfect matchings and graphs with certain degree and codegree conditions versus finding independent sets and hypergraphs with girth at least 5. And we also, in general, in settings where the Rödel's nibble could give you approximate decompositions, you can define the correct high girth analog using these forbidden matchings. So in our original paper, we explore Steiner systems, edge coloring, vertex coloring, rainbow matchings, Latin squares, and high dimensional permutations. Since this paper appeared on Archive, a number of groups have also used it to do things with Turon densities, and we even very, very recently, it's also on Archive, use it to prove a conjecture by Brown, Erdős, and Schoch as well. So there are a lot of potential applications. It's a very, very general framework, and I think a nice way of viewing a number of these problems instead of thinking about them in an ad hoc manner and the proofs sort of reinventing the wheel from scratch. For all these proofs, you can think of them as having a broader framework and in a broader context if you think about them as matchings in the appropriate auxiliary hypergraph with forbidden submatchings. So thank you for listening.
Great. Thank you very much, Michelle. So do we have any questions? Actually, maybe I could ask, you mentioned a new version of Telegrams inequality. Can you say a word about that? Or?
Certainly. So the details are also in the paper if you want to look on Archive as well. But it's a linear version of telegrams. So by linear, I mean linear in the Lipschitz constant. So I guess traditionally, in a lot of these things with the iterated absorbers, and even if you look at like the details of Bohman and Warnke's proof, they were using martingales and they were using certain tricks, including Friedman's inequality, to try to get sort of this linear Lipschitz, but Friedman's inequality isn't strong enough here for our concentrations. It kind of works in what we call the dense setting, but it's not strong enough to give us the results that we want. We have to do the concentrations in the nibble proof. So we'd actually developed this, Luke and I had developed this like 5 years ago and finally found an application where it was actually needed. So we were quite pleased.
Okay, thank you.
Yes.
You mentioned that the random greedy approach is sort of better for counting, and the nibble approach doesn't yet give that. I was just wondering, are there other examples of nibble things which have then been converted into counting results? Is there a sort of, I feel like I don't know this already, is there a kind of standard approach to try that might or might not work? Or is it
So there's this differential equations method in general, and a number of people have been sort of doing these, you can think of them as like random greedy algorithms. So like here, if you think about this in terms of the line graph union H, they could have formulated it as some sort of greedy independent set algorithm. So that's sort of been more of the thing, is to try to think about these things with a differential equation method. In their survey article on the nibble, I think Derek and Daniela and Tom and the others do talk a little bit about the counting, but I think it's hard because you have to have enough control when you're doing the nibble. And at some point we thought we might be able to do it, but we want to maybe think a bit more, because we hadn't initially been thinking about sort of the natural counting questions. So I mean, it would be interesting to know if it is able to do it. It's not clear to me that it isn't, but we haven't successfully managed to get it to work. But I guess people maybe more are using this differential equation method to do the counting type things recently. So the other group who did the Hypergraph Erdős conjecture also were thinking about Hypergraph Latin squares, and they have a bit better result than we do. They can actually they fully sort of, instead of approximate Hypergraph Latin squares, can find exact ones, and they also have very good counting estimates, but they're also doing more of this differential equations technique.
Thank you.
I think it'd be very interesting to see if the nibble approach could yield it as well.
Okay, any other questions? Okay, in that case, let me remind people that there's another talk in